Okay, so without saying any more, the first speaker is Professor David Evans, and he's going to tell us about quantum symmetries.
Okay, so I'm very happy to be here and share this occasion with Tony. We first met, I think, 40 years ago in this building. Yes. And our paths have crossed ever since. We were colleagues for some time in Swansea. I've been back here many times. Okay, so I'm going to talk about mainly joint work with Corey Jones on quantum symmetries. So this is about symmetries beyond groups or even quantum groups. And of course, there'll be two aspects to that. Well, one is how do you construct these symmetries? And the second one is, can you construct actions in these symmetries? So I'll be more concerned about the second part, actions in the symmetries. So that's the new one. But before I can do that, I have to tell you what kind of symmetries I'm talking about. And they were thrown out by this comes from theory of subfactors in operator algebras. So take your favorite algebra of operators. Say there's infinite tensor 2x2 matrices, and they're completed by representing it on a Hilbert space and then taking weak completion. So these are monomial algebras. So there are many ways you can complete that infinite tensor. Apparently, in fact, there are not many ways. So if you represent each M2 2x2 matrices on a Hilbert space and then take the infinite tensor, then if there's a trace on the infinite algebra, then that algebra is unique. And it doesn't matter if you have 2x2 matrices or 3x3 and so on, you get a unique algebra. That's the kind of algebra that's thrown out in statistical mechanics. But if you take a random representation of 2x2 matrices on each tensor factor, then you would not usually get a trace. And those algebras are the ones that come in quantum field theory. Those are the type 3 factors. So there's basically just two things. You get a type 2 with a trace, or this type 3 in conformal field theory. So the algebra itself isn't that important, because there's only one of them. So let's talk about actions of groups on these algebras. So say taking a finite group G and on the big algebra N, and if the action is non-trivial, if it's out there, then when you take the fixed point algebra, you can recover the group just from that inclusion. If you take the automorphisms of the big algebra, which fix the fixed point algebra pointwise, then that is exactly the group that you start with. So the inclusion encodes the group. So then what Vaughan Jones proposed was that when you look at inclusions in general, these encode more general symmetries. So in that way, you can then throw out more and more examples of symmetries beyond groups. So physics, conformal field theory, and so on, or even statistical mechanics, will throw out examples of these inclusions. But then there's also a converse issue. When you start with this inclusion, is there a physical model which explains that symmetry? So there's two aspects to it. Now, when you've got this inclusion, how do you encode the symmetry? How do you recover the symmetry? Well, how do you describe the symmetry just as I did for groups? So one way to do that is to take M as an NM bimodule or an MN bimodule. And then you take that and its conjugate and multiply that in all possible ways. So only 4 kinds of bimodules will appear. And just 4 kinds. And then we're only going to look at the situation which generalizes the finite group case, in that only finitely many bimodules will appear when you decompose them into irreducibles. In conformal field theory, that's rationality. Right, so we have these kinds of bimodules, and this can be described by graphs like this. So this is the situation for the symmetric group. These are one kind of bimodules, say MN, MM, these two are essentially the same by conjugation. So there's only one kind in the middle. So this is the group, that's the group dual. That's the picture for finite group. So the vertices represent bimodules, and the edges represent multiplication by the fundamental bimodule. So there's much more to the symmetry than the diagram, because this in general won't tell you what group you have, even in the group case. You cannot recover, even in the abelian case, which group you have just from getting out the group, or the 4. Okay, this is another example. The diagram here is E6. So there's 3 irreducibles there, 3, another 3 in the middle. Okay, so there's a group example and essentially a quantum group example. Okay, so that's part of the data. As I said, in the group case, you don't see everything here, so you need much more data to describe the symmetry, but that's usually done through 6J symbols. Some integrability condition, which often statistical mechanics will throw out to you from the Aernout equation. So, but in general, you don't have algebraic structures which throw out that integrability. You may have to do it by hand. Okay, so let's look a bit more at these group examples. So maybe I should have said before. Back here, there are 2 graphs appearing here. The one on the right and the one on the left. So the square of the adjacency matrix, either of those graphs, is what's called the index of this self-factor. It's actually a K-theoretic object. If you regard M as a modulo of the small number, that gives you an element of the K group. And that's the index. Okay, so the index for finite groups is obviously just the size of the group. Say, if you go down or you go up by symmetry, there's clearly G copies of N sitting inside here. So the index should naturally be the categority of the group. So you can only get integer indexes from finite groups. But there's many more integer examples than the ones which come up like this. For example, you can take this algebra here and put it inside basically itself, by tensioning on another copy of M2. In that way, you get 4 copies of the small algebra sitting inside here. So the index should be 4. If you change M2 to M3, you'll get more integer examples. There's something else you can do. You can take the subgroup of SU2 and let it act on M2, and then take a test product action. So then you take a fixed point algebra, and you get a square like this. So if the index is multiplicative, this index should be the same as that. And if these two indices are the order of the group, that means that this index has to be the same as this one. So that's another example of an index 4 subfactor. And in fact, there's a deep result of Popper that all index 4 subfactors rise in this way. It's not known for index 9, place SU2, SU3. It's probably many more subfactors. So they're classified by subgroups of SU2 and some cohomology. As subgroups of SU2 have a well-known classification. They're just affine ADE. Now that's still integer index. Now index less than 4 means you basically replace this compact group G by the loop group for SU2, and the cohomology that was present here then becomes a multiplier in the projective representations. Right? So the index less than 4 has an ADE classification. This is affine. This is one more word. The norms of these matrices classify all integer matrices of index less than 2 or 4, depending on whether you square it. Now, okay, so less than 4 goes beyond groups, but it's still basically formulas. So you got to go beyond 4 to get something more interesting. And there is a classification of all set factors between 4 and 5 and even beyond. Now, in the rational case, where there's only finite and many reducers, these are all the possibilities of index less than 5. So 5 itself is basically groups and subgroups of index 5. Then there are some things to do with formal embeddings of group groups. And then there are some possibly weird ones here. I'm going to focus on this example here, which is beyond the groups and one groups, the whole group subfactor. I'll write down that in a minute. So from that theory, I'm going to look at quantum symmetries described by these pictures here. So there's an A4 example, A6, and an E8. But because I want to act on different algebras, not the one that I started with, I only want to take the NN system, so the ones in orange. So here there's 2. Here I think it's 8. Here is 4. So it arises, the A4 example arises from SU2 level 3, SU2 level 15. But, or if I just take the even part, that's just G2 level 1. This is an old default. The E8 comes from an embedding of one group. So that's 2, 8, and 4. Here's another one. This is the whole group, for example. So these are the 2 graphs for the whole group. So there's 6 objects here, 4 there. Now, the 6 upstairs are represented by these fusion groups here. It's basically the symmetric group S3 or the dihedral group, if I ignore what's in red here. These relations just precisely describe S3. So it's something to do with S3, but it's worse than that. from these, you get non-integer indices. The dimensions, the dimension of the irreducibles is additive in multiplicity. So I can apply the dimension function to this relation. The dimension of alpha has to be 1. So that means the dimension of rho squared is 1 plus 3 times the dimension of rho. You solve that quadratic and you get basically this. So that doesn't look related to what I had before with 2, 8, 4, and I had 6. But there's actually only 2 orbits here. This is 1 orbit. So when I divide out by that, I will get this 2 in, and that's very convenient because what I really want to do is to look at actions. These form of symmetries are the non-commutative torus. And the non-commutative torus has K-theory, which grows with powers of 2. So the only way I will be able to get these to act on non-commutative tori is because the dimensions are powers of 2. Okay, so I'll come back to that later. Now, there's one other aspect I want from this, and that's say a bit more about loop groups. So stated as the Belinda ring level K for SU2. So, what's really going on with these kinds of subfactors here is that I'm looking at positive energy representations on the loop groups. And I can construct not just a factor, but a whole net of factors labeled by subsets of the circle. But by looking at those, the focus of the integral I, which vary in I, and a constant outside, that gives me a net of algebras. And in fact, conclusions like this, I prime is complementary. But if lambda is the vacuum representation, trivial representation, this is not an inclusion, it's actually an identity. It just defines what you want a particular object. And then I can identify this inclusion with a bimodule or an endomorphism of the original algebra. I'm mixing my metaphors here a bit. If I have an endomorphism of these type 3 algebras, which I'm quantum field theory, an endomorphism gives me, okay, an endomorphism gives a bimodule by twisting the action of one side. But for these particular algebras, every bimodule appears in this way. In other words, you can switch back and forth between the language bimodules and endomorphisms. They're equivalent ways of describing the same structure. So, okay, then this is, I can think of this describing the representation theory of this net. Of course, if I have one net like this, and I have an inclusion like I have with SU2, G2, and so on, I can get the inclusions of nets of factors. And I can induce endomorphisms here to endomorphisms. That's this theory of alpha induction, which is like this. If I take an endomorphism downstairs, which is a bimodule, I write down this bimodule. This becomes a natural bimodule upstairs. I want to add a gradient. I want M to act on both sides here. Obviously, acts here. For it to act here, I have to interchange. That needs a gradient. Gradings come in pairs. If you go one, you go opposite by reversing all process. So that means there's 2 inversions. You don't see this in the usual Mackey induction group theory because then the grading is trivial. It's a symmetric grading. So there's only one Mackey induction. Okay, so you can induce from sectors, you have sectors of space. But what's important is the common ones. Because from those you get modular invariants. Which you want form. So if I take two inductions, decompose them into irreducibles, count the number of common ones in this, in other words, what really is there, then you get a modular invariant. And so what's important is the intersection to get the symmetries upstairs. Okay, so that there's also the so there's alpha induction plus alpha minus intersection. There's also the full system. And here's an example coming from SU2 inside G2. I've written it out in the language of SO3 rather than SU2. Ignoring half the objects. So in that case, I have this modular invariant. The full system looks like this. This is the picture I had in the other sheet, but I rotated it 290 degrees. So there's two induced systems described by this even part of the 8. So one is going down here, the other one is coming up there. And they intersect on the blue ones here. So that's this G2 level 1. So this has the fusion rules of the E part of the 8. This is another E8. This is G2 level 1. And then when you use these, 4 objects there, 4 objects there, you multiply them together in all possible ways, decompose into irreducibles, and you find 2 new irreducibles out there. So the full system has 8 objects. So that means this is another example where you could hope to try and let it act on a non-symmetric torus. So the 2, the 4, and the 8. So with the 2-dimensional, 3-dimensional, 4-dimensional torus. Okay, so I submitted my case. So I'll just say a few words about that because I needed to describe better the non-commutative torus. So K-theory is about, if you're talking about spaces, it's about vector bundles. So if you have a vector bundle over space, you can take the space of sections. Then that is finite projective logic. And that's an equivalent way to describe vector bundles. Now, if I were to replace this by non-commutative algebra, you keep this picture here of modules, and then they look like this for projection in the matrix algebra. So in other words, vector bundles of the spaces are replaced by projections in matrix algebras. So this has a notion of addition. You can add projections and we actually add modules in the objects. That gives you a semi-group. Now, the K0 is the group generated by that semi-group, so you're going to take formal differences. But it means that K0 is an ordered group. I'll use that over in a minute. Now, K1 looks a bit easier. It's just unitaries divided by the connected component 1. these unitaries and matrices divided. These things, yeah. This is already. I don't have to take differences because if you've got a unitary, you've got the conjugate. Now, so the problem we're going to look at is if I have a fusion category C, this system, the NN system, abstract system here. I can look at all the possible dimensions. Just as we have for group examples, so there is some irrationality. I define the group generated by dimensions. And then the question is, if you've got a tensor category C, as in the example we have, can I construct an action of that category on C-star algebra A with the same cases? And by action, I mean as bimodules. Of course, you'd also want it to be outer, non-trivial in some sense, but often that comes out automatically because of the irrationality. An irrational bimodule cannot be equivalent to a trivial bimodule. Okay, so this is one example here. I take the whole group system with these fusion groups and these dimensions. Can I construct action on C-star algebra with that K naught, but some non-trivial K1? But before I delve into bimodule theory, there's some parallel work on modules, which goes back to free-hot-place element. So if you take the example I had, SU2 level K, positive energy ramifications, then they described that Berliner ring through twisted equivariant K. So I just sketched working by K theory. So you have to throw in these extra equivariants to a group in the background, and it's twisted by some kind of cohomology. So what they had was bundles of compacts over the bundles of compact operators living over the compact group, which is equivariant for the group acting on the base by conjugation and upstairs by some non-trivial action. And the twist, the projectivity of the loop group comes through having a non-trivial bundle. So how you measure that bundle measures how far away you are from the mechanical representation of the loop. So that means that there's a picture of the Berliner ring through twisted equivariant K theory. Now, one thing I'm doing with Ulrich Henning for some time now is to replace the algebra compact operators by more exotic operator algebras. And actually, you get higher twists beyond Fried-Hopkins and candidates for more exotic conformal field theories. I'm not going to go into that today. There's another piece of work from a postdoc, Andreas Olsen, where we saved. We can do what I want to do with modules by constructing algebra which reproduces the K theory, the dimensions as modules. That includes temporally linear. There's a possibility for applications. Okay, so that's it for the background. These are the results for non-commutative toric. So, what do I mean by a non-commutative toric? So it's the universal algebra generated by two unitaries satisfying this commutation relation for a fixed theta. Now, really interested in the case when theta is irrational. In that case, you don't have to worry about universality. Any representation you C star, it's simple, no ideals. And it's vastly different from the case when theta is zero, universal algebra, this continuous functions in the two terms, which has non-trivial k1 because of the winding ring. And that persists for any theta. Even if theta is irrational, it's still okay. On the top of these variables. Okay, so that's k naught is two copies of the integers, which I write like this. Now remember I said k naught is really an ordered group. So it comes with a natural semi-group. And the ordering is given by this equation. So in other words, the positive elements here are these pairs, which when thought there was a real are positive. That means I can recover theta from the ordering. So the ordering is important. It's just not just a group, it's an ordered group. I have to keep track of orderings all the time. Now, one of the tools we're going to use to construct these symmetries goes back to an old result mine with George Eliot, where we could show that this non-commutative torus, when theta is irrational, always has a decomposition in terms of matrices over the circle. And that's the best you can hope for, because this clearly tells us it wants to have K1 and K0. Z2. And the actual so this is enough time. How do you get projections in rotation algebras? I think continuous functions on one torus L2 of the circle by multiplication. So I can write down the characteristic function. Now that's a projection, but it's not a continuous function. So it cannot probably help. But if I were to try and make this continuous, I join that. Call that part of the function f. So I've got the characteristic function which I started. Then from that big F, I can write down a 2 by 2 matrix. Big F is between 0 and 1. And then this thing here is a projection. It's self-adjoint and it's idempotent. Now, F I think of as multiplication of L2 of this interval. And I think of this matrix as actually two copies of that interval. But I put the second copy here. Okay, so that means I have two projections which live on orthogonal pieces. So the sum is a projection. And if I look at the diagonal part here, I've got f 1 minus f. This bit in the middle is 0. So that this little f is a continuous function. And then I have these remainder terms coming from the off-diagonal. So just take this function, multiply against here from an interchange. It's really the same function. And big F itself may not be continuous, but this combination is continuous. So that means I end up with an algebra with an element like this, where G is the off the Aernout. And I can affect the interchange because this G only lives on the small part. I can affect the interchange by translation. So if I use V to translate by this distance here, I will get an element of a rotation algebra. The trace is just the dimension of this thing is just obtained by taking the area and the curve. Well, this thing fits exactly over there, so the area and the curve is distance. You translate it, so that gives me irrational dimensions. Okay, so I've got two kinds of projections. This one, the trigger. That's all I need. Okay, now how can I act on the non-committed Dorlas? So let's take a simpler one and hopefully the golden mean. The whole group is similar except is a 3. So I'll take the golden mean, that's G2 level 1. And I have this relation, which I can iterate. And you get this continued fraction as such. Now, from the continued fraction expression, you can write down inductive units. I can write down this ordered group as an inductive unit of these ordered groups. And from that, in this work with George, we could describe non-computed Dorlas as an inductive using continued fraction expressions. This is a fairly general example where I have the same look for continued fractions. Goes back to the differential. You have this quadratic relation. Okay, so this is what we can do. So it's just appeared in CNP. So we can construct an action of the Borel system on non-commutative Dorlas, satisfying that relation. It uses a number of ingredients. One is the theory goes back to George. But it needs something else because I have 6 irreducibles here, and I'm really describing the non-committed Dorlas with the right 2 objects. Now, I talked about the whole group subfactor with a 6 and 4. There's another subfactor which has these 2 graphs. I've written them separately instead of next to each other. So the H2 is this system up here. H3 is another system with these fusion units, but it's a different category, 6J signals. Right? But there is a subfactor with these 6 objects here for H2, these 6 objects here for H3, and then there are two things here which are basically the NM of H2, H3. And it's those 2 that you use to get this action. It's really coming from an orbit where I identify these and identify them. That's how this is constructed. Okay, so that's, I think I'll skip that. Okay, now, higher rank. So this gets trickier because the K-theory is harder to describe. So, but at least This is the description for a high-dimensional non-commuted torus. So you get a finite number of matrices satisfying these commutation relations pairwise, where this theta is a matrix, but it's not a skew-symmetric matrix. So if I take them pairwise, I have at least one projection of one element of occasion coming from the elements of the and then pairwise, when we take these R's and S's, so taking all the possible values of thetas, I will have this number of degrees of freedom. Those are the ones for which I can write down projections which construct the final. But the K theory is bigger. The K theory grows exponentially. This grows polynomially. So you're lucky at the beginning that they are the same. So for n equals 2, n equals 3, the numbers I get here and here are the same. But once I go to 4, there's a missing dimension. So how do I find that missing dimension? That was solved by George in 84. It involves looking at the range of the trace through this exponential exterior derivative. So for small n, this is all we need. But higher up, these exterior powers come in. And it's what I need to describe the single dimension. So that comes in through Pfaffians. So and I'll need this in a special case, n equals 4. Okay, so these are some non-actions which we describe. So first of all, this is emphasizing the point. If the rank is not power 2, then there's no action at all. At least when all the dimensions are rationally independent. Now, here's a more interesting example here. So the obstruction for the existence of these actions is number theoretic. And these strange looking conditions here, but if k is 15, 15 plus 2 is another prime. But 15 plus 1 is a power 2. So this obstruction does not hold when k is 50, as we'll see in a minute, where we can construct an action. Okay, so I talked about G2 level 1. Now we have a rank 4 example. So this has these fusion rules, and of course, at the end at G2 level 1. And then the dimensions are rationally independent, and we can construct a dimension of this system on a non-commutative 3 torus with these rotational. Okay, so it's convenient there that they're rationally independent. Now, here's the one with related to k equals 15. Now I've got 8 series. And so I can write down a matrix like this. So I've got 6 objects here. And then I've got the trivial bimodule. So I've got 1 plus 6 is 7, but I need 8. So this is when the problem starts. So if you I could write down these are quantum dimensions, or the dimensions of 6 of these 7 as ones. So if you write them down like this, I mean, no one particular one, then a miracle happens. If you take, to get the missing dimension, you take the fat field, which looks like this. And then, lo and behold, that gives you the missing dimension. Right, so this is not true for all Q, it just happens to be true for this Q here. So that's computation I don't totally understand. Mark Riefel had an explanation for the diagonals beyond the obvious ones by the geometric picture. So I think one should go back to that and see what that actually says in this example here. Otherwise, it's a bit unsatisfactory. Okay, so then we get that. And then now I go back to the example. So I've now constructed an action in this 2 blue parts on 2-dimensional torus. This on 3-dimensional torus, and this on another 3-dimensional torus. And then the question is, can you construct an action of all that on 4-dimensional torus? Giving a picture like this. So this isn't quite finished. This is what I expect. There is a 2-dimensional torus, 2 3-dimensional torus, and 4 which sit inside each other like this. So these actions are correct. What's still missing is proof of this construction here on 4 torus. The problem is that these, one of the issues is that the dimensions are not all rationally independent within 0. So some of the techniques don't go through it. So it needs a bit more work. But I believe that's describes this example from the field theory. Okay, so I think I'll finish there. Okay.
I think we're ready to start the next talk. And the next talk is by Hans Maassen, and the title is Copying Quantum States. So over to you, Hans.
Well, in the first place, thank you very much for this kind invitation to this beautiful place, which many of us have very fond memories of. I'd like to talk to you about a simple subject, so just sit back and relax. It's about copying quantum states, and anyone who has heard something about quantum mechanics knows that this is impossible, right? So I have to say something more about that. All right. This is known as the no-cloning principle. And the no-cloning principle says that an unknown quantum states cannot be cloned. And this is not of course true. If you have a quantum system, you don't know the state, and it's impossible to make 2 systems in exactly that state, which in the tensor product effect of those 2 states. This principle was discovered in 1982 when I happened to be there, so I have good memories of it. It was invented by Dick Hoeksma and Dennis Deeks, who discussed about it in the Quantum Club in Amsterdam, 1982. And Deeks wrote it up, and he has the name now, Mr. No Cloning, and Dick Hoeksma became a teacher. Anyway, I consider him as one of the no-cloning persons as well. And the other 2 are Wootes and Zurek. They invented the name, no cloning. Right. Now I'm going to reformulate this principle a little and also extend somewhat. Because even in the textbook you will not find exactly this statement, but there you will find another formulation of no cloning, which in fact says An unknown pure state of a system can be cloned if and only if the system is classical. So this word quantum has been enlarged to this if and only if clause. Can only be done if it's classical. And already on this level, you find often in discussions of this principle confusion. Some physicists would maintain that also classically cloning is impossible. Then there is restricted cloning. I've invented this name for the occasion. And this is the textbook version. It says that the state of a system can be cloned if and only if it is known to lie in a given family of states which disjoint supports. This is a difficult way of saying if they are pure states, then the state vectors have to be orthogonal in order to be able to clone the system. So you get a system and you know that the state is in one of a certain set. Then if you can find out which one it is, of course, then you can clone, just make a copy. You just make two of them. Right. And the pure state version is the one you will usually find as the no cloning theorem, for instance, in Nielsen and Schwann. Okay, then the third one is restricted broadcasting. And that is not about pure states. And it says that the state of system can be broadcast, and that's a slightly wider notion. Cloning, that means that if you have a system, you can produce a pair in a tensor product state. Broadcasting means you can produce a pair such that each of the marginals is equal to the original. But they don't have to be independent. In fact, independence is funny. Okay. Yes, a state of system can be broadcast if and only if it's known to be a convex combination of certain disjoint ones, that is, clonable ones, according to the previous theorem. And the only thing I want to do today is to explain what this means exactly, and also to prove this. And why should I bother you with this? Because anyway, it's not new at all. Moreover, 1 and 2 can easily prove from 3. And the problem has been treated in even more generality in 2015. However, it's a very fundamental subject about which some confusion is always luring about. So when we wrote our textbook, Burkhard, Humer and myself, we decided we had to describe this in some detail and maybe more correctly. And this will appear. But in the meantime, I also published it in a volume devoted to Partnerserraten, and I'm giving a talk about it. The reason why this is useful, I would say, is that if you include the classical case, then it becomes more clear what the statement is. And that can be done by using matrix algebras. So instead of the ordinary open space formalism, I will use the formalism of matrices, of observables. On finite dimensional open spaces, I will only talk about finite dimensional open spaces. And the inspiration of this treatment comes from Lindblad, who died 3 years ago, Göran Lindblad. And moreover, I want to give a more difficult but more careful proof of the textbook version, and because that's oversimplification. And also I want to give a more transparent proof of the restricted broadcasting, which is surprisingly complicated. Everyone who sees this paper of Wine, Case, Fuchs, and Schumacher wonders how can no cloning be so difficult? If the pure state version is so simple, why should mixed states be so difficult? It's a very difficult paper, but I can tell you. It uses fidelities, etc. And I try to do this in more transparent way. So I have developed some language, and it's the language of matrix algebras and completely positive maps. The algebra of observables of a system is a star subalgebra of MD. So I'm not assuming it's all matrices, but it is a star algebra, and it contains the units. The state of system, you probably have heard about this anyway, but is a linear, functional, which is positive and unital. The state space is the set of all states on A, and this is the set of extreme points, E or A. So, for instance, you can have A equal to all matrices, D by D, and then the state space is well known. It is just a set of density matrices, positive matrices with transform. But I make a distinction here between the state phi and the density matrix rho. And the extremal points are given by the vectors in the Hilbert space, or the one-dimensional projections for rho. Right? There's another example which is important. Namely, if you take only the diagonal matrices, then the state space is just the set of all probability distributions on D points on the diagonal. And the extremal points are the delta functions. So in this case, in this sense, classical has been included into quantum, and I think that's the proper strategy to discuss quantum mechanics, to see it as an extension of classical mechanics, not as something completely outside. The diagonal algebras are isomorphic functions on a set of D points, which I will call omega D. And this is the correspondence. And of course, the states on FD are given by the probability distributions. Okay, this is what I'm saying now. And the classical case can always be recovered by taking the algebra commutative. So that's the objects we are looking at. Now we are looking at the arrows, the operations. And why do we have to consider those? Well, because if you want to prove a no-go theorem, then you have to, then it's not enough to know a lot of examples and see that each time it's impossible. No, then you need a delineation from the outside. What is possible? What can be done to a quantum system? And that's precisely the so-called quantum operation. The quantum operation of unital, completely positive map. T, from one algebra A to another algebra B. I always denote by pictures like this, and note that A is on the wrong side, so this is the direction of T. But it has the, if you do it like this, then it has the advantage. It can also read it in that direction, and then it acts on states. T is positive, if it maps positive matrices to positive matrices. Completely positive, if that is robust on the tangent with something else. And it's completely obvious that you have to do this. However, what's not obvious is that this is an extension. This is really stronger. It is stronger, and that's because of the possibility of entanglement. So complete positivity is better and more important notion in quantum mechanics than positive. And it's called unital if it maps to the actual unit. And that's just conservation of it. We consider two possible pictures, a Heisenberg picture and the Schrödinger picture. I'm standing in this building, so this is the Schrödinger picture. It maps the state only to the state phi, composed with the T, also called T structure. That's a state on it. So it looks the other way. And in general, the Heisenberg direction is the mathematical direction, and the Schrödinger direction is the physical direction. You can understand what's happening if you go from left to right, sorry. And you can do calculations to go the other. Well, okay. I can just add that they form a category. The star algebras, the matrix algebras, together with the completely positive unit maps, form a category, which are called QP. Not very important, but it's a category. And yes, if an algebra A would be completely identical in a drawing, usually denoted by a straight line. For instance, A POVM looks like this. This is a measurement. Just any quantum measurement of any of this form, because it takes a state on A and makes a distribution on outcomes from that. If there are any questions or if I'm making something unnecessarily complicated, tell me. Now, it's well known, probably most of you know this already, so I'll be quick about it, but there is a characterization of all completely positive maps devised by Steinspring, and it says that if you have a matrix subalgebra of MD, and there is a completely positive map to MD prime, then there exists a Hilbert space and a representation of the algebra on that Hilbert space, such that T can be written in the form V star pi of A V, where V is the isometry. Isometry from C prime to A. This is not the usual form. Usually people will write here instead of pi, will write a tensor product A of pi A with 1. And that's indeed the case. If A is MD, then the only possible representations are of that form. But this is more general. And sometimes you need it. Well, I go very quickly through the proof. This is Steinspring's original proof. He defines all of this bigger space, A tensor of C D prime, the quadratic form, divides out the null space, and then it turns out that in almost trivial way you can define the natural representation of A on that, but also a very natural isometry. And if you do the calculation, which I won't do here, then it turns out that indeed you get precisely that's Steinspring. Now I'm trying to explain things not only in matrix in mathematical form, but also in diagrams. And then I need to introduce a few small simple notions. For instance, the matrix algebra M1 is just MC, of course. And that can be interpreted as nothing. And there's only one state on nothing. Now, operations towards and from the trivial algebra are the following. You can map A to C, and that is, of course, the state. And you interpret that this is the implicit map. Here you have nothing, then you do something, and then you have something in the state. And altogether, it is the state file, creation of state file. But in Heisenberg, it is just a state file. In the other direction, we have this. Reduce, this is nothing. Throw it away, forget about it. And there's a completely positive map from C to A, which maps the number Z to Z times 1. And it's nice, and when there is a mathematical fact, maybe that there's only one thing of that type, but there are many of those. And it corresponds to physical fact. There are many ways to prepare a system, but there's only one way to destroy a system. Yes.
You say many ways to prepare a system. Is it many ways to prepare different states of the system or the same state?
No, many ways to prepare a system in a state. So there are many states. Yeah,
many
that's what I mean. Yeah.
You can prepare it in different ways.
So. I have a table. There's nothing on it. I buy something in a shop. I do something. Put it there. That's a preparation. And then it's prepared in a state. And the difference is only in the states. Well, there's another way of saying Steinspring, and that's the corruption. which says that if you have a phone A to itself now, this time, you can do that by creating some external system, so-called ancilla, then evolve unitarily for a while, and then throw away again the ancilla. Then something has happened to A. And the statement is that anything that can happen to A can be brought in this form. Anything. All right, now we come to our subject. It's copying quantum states. I will use three terms. There's copying, the non-technical term. There's cloning, which is a technical term, and which means that if you apply C on phi, or in fact, I mean this is C star phi, but also phi after C, is equal to the tensor product of phi with itself. A completely positive map, which in Heisenberg picture has to work from A tensor A to A, just the wrong way around. You want to double up things, but that's only in the Schrödinger picture. In the Heisenberg picture, you are going from A tensor A to A. This is a cloner. Now there is something funny about this definition. This is generally accepted by all physics.
Why do you say that the cloner works on the double to the single? I would think it's the other way around.
The state.
Well, you see, that's in this is the Heisenberg picture. Well, let me just this is the picture. So I have in the Schrödinger picture you can read it like this. I have the system in a state. I do something, then I have two systems, same parameter.
Yes.
Then that's the same as if I had two independent systems of that kind.
Yes, but then I would say that the outcome is in the product state. Not
So the outcome is in the product.
That's why I was wondering that in the first line.
Well, this is, you can also read it that way. And that's the Heisenberg picture. See, then C goes from the tensor product back to A. This is this duality between Heisenberg and Schrödinger. It's a bit getting used to, but on the other hand, it works mathematically very nicely. But this is an important point, yeah. Now there is already something funny about this definition. I don't know if you realize that. You require the copies to be independent. Copies are not independent. If you copy a thing, you get the same. You don't get. I mean, if you would input into a copier a probability distribution on copies, then on the outside you would get, well, the probability. The first probability would get a pair of those. The second probability would give a pair of those, etc. You would not get the product distribution on pairs. So as a definition of copying, this is already funny. In quantum mechanics, it's reasonable and it is also valid. It is the right definition when you talk about pure states. But you must realize that you're already doing something funny because even pure states in quantum mechanics are not certain. They have some spread. So the whole idea of copying does not really fit to the idea of cloning. And it's a source of the confusion in discussions about no cloning. So therefore, a new notion of copying was invented. So we have now three notions. Copying is a non-technical, cloner means different, and broadcaster means the following. It's also an operation from A tensor A to A. But now these are requirements, and in the picture it looks like that. And in the Schrödinger picture, that's very easy to read. It says you have to do something to it. You get two systems, but if you throw one of them away, doesn't it which, then it is as if you have done nothing. This is really, I think, this in fact what copying should be. And this is called broadcasting nowadays, and it was introduced in 1996 by Byron Case, Schumacher, because they also wanted to discuss mixed states. Of course, this is a special. But you see here the requirement that the copies are independent does not play a role. You only require that you get two systems and the marginals are equal to the original state, but they don't have to be independent. Okay. Well, okay. In the case of pure states, cloning is the same as broadcasting. And that's why you can, without being punished, use this funny definition. Why is that so? Well, in one direction, it's obvious. Clone something, then it's also a broadcasting action. But the other way around is not completely trivial, because then you have to use the purity. Suppose the right marginal of phi composed with C is equal to phi itself. Choose a projection in the algebra, then we can write as a sum of two positive functions. We know that these are equal because of broadcasting. That's what we assume. So now we can this is 1 into p plus 1 minus p. And then here we have two positive functions of a, whose sum is phi. Now, if phi is extremal, then that means that it's extremal in the clone of all positive functions. It means that these must be proportional, both of them must be proportional. Well, then if you realize that phi must be, that this lambda, this proportionality function must be phi p, then you see that you have this, and this is almost, so, because the projections span the whole algebra, we may conclude that phi composite C is indeed tangible. But that's only because of extremality. Now I'm starting. Here's the first theorem. For a matrix algebra and a unit of completely positive map, C, from A tensor A to A, the following are equivalent. C clones all pure states. C broadcasts all states, not only the pure ones. And A is abelian, it's commutative. And moreover, C turns out to be just the multiplication in the algebra. That's probably something surprising. This is the classical cloner, or the classical broadcaster. It's just the monobit, as category people would say. Now, in order to prove this, we need Dyson swaps, and I think many of you know this, but I'm going to formulate it anyway. If you have a completely positive map for A to B, unital, then it satisfies this inequality in the sense of completely positive maps. C is T of A star A greater than T A star A. Moreover, if you have an A, well, this is not just an equality, but an equality, then you can extend that. Then A is multiplicative, and this all B, you also have this equality. That's multiplicativity. And then proof is not so very difficult. If you have no Stein spring, then the equality, the above equality, then you get it. But then it just says that 1 is greater than VV star, and V is an isometry. So VV star is projection. If you have equality, then it means that this vector here, if you act on the vector, this vector here has to be in the range of this projection. But if it's in the range of the projection, you might just as well write this in front of it, and you get the multiplicativity result. Okay, now I want to prove the first theorem which I announced. From A to B, that is, suppose C clones all pure states. then of course it also broadcasts them, because for pure states that's the same thing. But now we can extend this equality by convexity. So it holds for all phi. For B to C, that's the real work. We have this broadcasting relation for all phi. Well, because it's for all phi, we also have this operator equation. Now I'm going to do a small calculation. Consider C of A times 1 star A times 1. I can just multiply inside. Then using this for A star A, you get this. And then for each of them, you can split out again. And overseeing this, you see that A times 1 is apparently multiplicative. Because you have Cadison-Schwarzschild equality. Then we can do another calculation. Take A, that's this, by broadcasting. Then I can use non-conductivity. Then I can just multiply inside. I can do it the other way, because these all words commute. And whether A and B commute or not, A tends to 1 will always commute 1. So I find that A and B is equal to B, and moreover, it's equal to C of the tensor products. Now that's the work. Now we've done it. Only have to check that if you are in this abelian situation, then indeed C clones all pure states. Well, that's easy because the pure states on a commutative algebra are just the delta functions. And these are certainly, well, it's trivial calculation to see. Yes, if you apply delta I to C of tangent G, because this is the product, and the delta I on the product is just Fi of GR, then you can split out again. You see that the deltas are indeed growing. Now, what we have met in the meantime, very good idea, thank you. What we have met now is the so-called classical copy, which people don't usually talk about, which is important. Otherwise, this whole British theory couldn't be formulated. And we have now seen already 3 forms of the classical copier. It is the product. It clones the deltas. And also, if you replace this with a 2 variable function, then you get just evaluation of the diagonal. And that's why it's called copying, right? Because if little c is just copying on the set level, then of course we can screw up this composition with this trivial copy. And this is the diagram I'm going to use first. And so I won't block here just this thing because it suggests copying. And again, it can be read in 2 ways, right? In this direction, it's multiplication. That direction is from all the pure states of the deltas. And it's important to note that this is, yes, it is a universal broadcaster, but it's not a universal cloner. As I said already, if you put in one thing, already 1/3 and something else with probably 2/3, and you apply this classical copier, you get this solution. So with probably 1/3, you get a pair of zeros, and with 2/3, you get a pair of ones, but you don't get the of course. That means that if you take cloning seriously, Even classical systems cannot be cloned. And cloning is not a difference between classicality and quantum. So you should take the other definition. Okay. This is the standard formulation in the textbooks. If you have a d-dimensional space, a set of pure states, or vectors, then if they have a common cloner, the vectors must be orthogonal. And as I told you, it's usually presented as if this is a triviality. It's not completely so. It's usually done by assume you have a unitary which does this, and it does it also for, let's say, two different vectors. And these vectors have to be orthogonal. And there is a small calculation which shows that. But it doesn't mean anything. I mean, what's this funny E? Why is this the only way of copying? Of course, it's easy to repair, and it has to be repaired by using Steinstring. Steinstring says that the clonum can always be written in this form. And then there's a small calculation telling you that this is the case. And that means that the range of V must be in that space. So V psi must be the form psi that's psi. And something in CK unit vector. So let's say that unit vector is alpha. And then the reasoning is almost the same as in the textbooks. Namely, two clonable vectors have a scalar product which is given by the product of psi prime. Then I use the factory. And then you find that it's squared sometimes this net product. And the only way in which that can be realized is by taking psi scalar product psi 0. So that's the standard form. Now I would like to formulate the main result of this talk, which is the result of Barnum, Case, Fuchs, Rorschach, Schumacher. When can any set of states be broadcast? So we have a set of states on a matrix algebra. Statement is the following: these are equivalent. The states have a common broadcaster. There exist thetas with orthogonal supports, such that all the states are convex combinations of these. And equivalent to that is just that all the density matrices of the states in S commute. This is well known. I mean, this is what people know. This is the mixed state no cloning theorem. And this is the thing which has a terribly difficult proof, which I want to simplify. Okay, I'm first going to prove the equivalence of B and C, because that's easy. Since the thetas have orthogonal supports, that density matrix must be, so also the convex combinations of those. And from C to B is also easy, because you can simultaneously diagonalize all the rows, and you get the commutative algebra. You take the minimal projections in that algebra, and then just for fun define these states. This is not unique. There are many ways of doing this, but this is one way. So these are the states which are on the blocks. So the rows are all commuting, that's why they are all concentrated on blocks. And if you take a state which is looking only on that block, volatile I, then of course these states are disjoint, but also they reproduce. they have this any state which is a complex combination, and then you make a clone by just doubling the data, and you have a broadcast. So this is from B to A. Now the difficult part is always, and this people usually don't realize, namely that there are no other broadcasters. And that's A to B. And for that, I need some more lemma. Okay, we call the set of states faithful if all of them vanish on all positive elements, then on one positive element, then that element must be zero. And observable is invariant. Well, of course, if TA equal to A. The state is invariant if phi composed with T is equal to phi. Now the lemma is the fixed point algebra lemma, which many people know in matrix algebra, but it's not well known. If T has a faithful set of invariant states, then the space of invariant observables is a matrix subalgebra wave. The point is that it's an algebra, closed under multiplication. And now, suppose we have an invariant observable A, then also its joint is invariant. And now if phi is invariant for T, we can say that phi equals star minus star A, which is of course this, is zero because you see. Sure. Oh yeah, because phi is invariant, sure. Just the invariant. Phi is a zero. But on the other hand, this is positive. Well, that is a switch because A is equal to 3A. And it's invariant of the observables. And if phi vanishes on a positive element, then that positive element must be zero. So TA A star A is equal to A star A. And then it's not difficult to show that not only this holds for A and A star, but any pair. So if A is in the invariant algebra, then A star is also, and also A star A. And that means that it's an algebra. Okay. Now here comes the hard part, which is, I claim, less hard than the part in the original paper for this theorem. And I hope you can follow it now. Okay, the hard part is that the only cloners are of the given form, only broadcasters. Suppose we have a broadcaster C for all the states phi in the set S. We make an assumption, namely C is symmetric, not important. We can always symmetrize. Suppose the support of S is 1. Also not very important, although you have to do some work. You can restrict the algebra to S with S. Now we have that CA tensor 1, one tensor is symmetry, and we can call this the marginal map. And the cloned observables are now the invariant elements of the marginal map. What that means, since S is faithful and invariant, that the marginal subalgebra is a star algebra. Oh, sorry, the marginal map set is a star algebra. You might think that's not very important, but it is, because we can now conclude that C is a broadcaster for star algebra. Now I wonder if anyone said, "Oh yeah, we have seen that before." That was theorem 1. There only exists a broadcaster for star algebra if that star algebra is commutative. So now we know that the invariant set is a commutative subalgebra. And then you're home. The rest of the work is nothing because, well, we take minimum projections and the star graph. We take the according projection onto that creates some work. And every element is a linear combination of projections. And its coefficients are states. And then we have our thetas. And the thetas are disjoint. And then it also follows that phi is the convex combination of thetas because of this. Identify phi. Then phi is the same as phi equal to E because it's according to the projection. And we found this convex combination. So now we have proved that in the case that we have a broadcaster, the states are all convex combinations of certain disjoint states that. Here's an extra, maybe not so important. I have some time. It may happen that they have a common cloner. Then the cloners are the thetas actually. So the cloned states must be disjoint. And that can be done with the means which are developed for theorem 3. And you just see that the only possibilities are the thetas themselves. Because the cloner has this property, therefore, Pi squared. This is the clone state. This is the product. So this is phi Pi squared. This is phi Pi. And therefore, phi Pi can only be 0 or 1. And that means that in this convex combination, only a single one can survive. Right, so that's really easy now. And our set of states must be a subset of the thetas and must have disjoint sequence. And in words, it just means the only way, the only situation in which you can do cloning is by just distinguish the states by a measurement, a polynomial measurement, and then just produce two of the states which you know you have found. It's trivial. This is the reason why most physicists feel that no cloning is trivial. But it's in one direction it's easy, in the other direction we have to do something. Let me give diagrams for this. See, if states possess one broadcaster, then they must satisfy this. In fact, it's definable. And that can be written like that, which is much more suggestive. Here's a polynomial measurement, this is a classical algebra, and here's a reconstruction. So if the phi is in SK all pass through this channel, and in Dutch we say they can glue over the classical region. Then you can also rebroadcast. And in fact, the broadcaster is easy to make. It's this one. This is the definition. This is the definition of C. Since they pass through this channel, we can use this classical intermediary part to make a classical copy. And then we just use two reconstructors. Yeah. So that's in fact the whole take-home message. If a set of states passes through this, then you can also make a broadcaster for them, but only in that case. Only in that case. Well, I still have some time. Oh, okay. I can give a second argument for Theorem 2, which says that cloning of set of states is only possible if it can be distinguished by measurement in quite a different way. If two different states on a star algebra can both be cloned by the same cloner, they have disjoint supports. It's a statement. And you can use the cloner to prove that. Namely, suppose the five that are both cloned by C, then you can repeat the cloning and you get an arbitrary number of clones, and they're all independent because it's cloning. And if you have a lot of independent copies, then you can do by statistics a distinction. And to make this more formal, suppose you have an n-fold cloner, and suppose that phi and theta are not equal, then there must be a projection on which they are different. And take that projection and its complement. Now consider this expression. Let's sit back from again. It says it's a sum over all alphas whose sum is equal to k. So this is the event that after the n-fold cloning, when you do all the experiments, each time you experiment in one, the number of successes is k. This is just a classical probability, and you know that the evaluations, the values which each figures take on the phi and theta are binomial distributions. And since they are binomial distributions with different mean, they become more and more disjoint. If you define the test operator, which sums up Q's only to 0 and the average number, expected number, then this Tn is able to distinguish them. You don't necessarily have the probability to do, but anyway, it's sufficient that you have this sequence that is only possible if I find that that's disjoint. That was it. Congratulations.
Well, thank you very much for the invitation, and I'm very happy to be here. I have fond memories of Dublin, even though I never was there for a very long time. And I want to start with saying that my talk is somehow orthogonal to that of Hans Maassen, because Hans was talking about finite quantum systems, and I'm talking about infinite classical systems. So, and here I wrote the people is who I did the work. Rodrigo Bissacot from Sao Paulo, Eric Endo, who was our joint student, who was now in Shanghai, and Arnaud Remy from Paris, who also told me he spent a pleasant time in Dublin in the past. And another paper is Rebecca Fernandez, who is in Shanghai, Yevgeny Verbitsky from Leiden, and his student Mahmoudov, who just defended his PhD and is on his way to Finland now. Okay, so Dyson models are, well, if some people complain about the name because he didn't invite them, but then Ising didn't invite the Ising model and Post didn't invite the Post. So what I will mean by Dyson models are one-dimensional long-range variables. And I want to basically address two questions which both have something to do with a one-sided versus two-sided point of view. The first one is the G property versus the Gibbs property. Here to compare what a measure where is it described by the influence from one side or the influence from two sides. And this somehow is between the dynamical systems point of view, as developed by Sine, developed by Bowen, and a statistical mechanics point of view on the evolution method. And the second is to compare systems on a half line and the whole line. And I applied that into two somehow different type of questions by random boundary conditions in low temperature and some properties of eigenfunctions, transfer operators at high temperatures. So first about the one-sided versus the two-sided influence. So the stochastic systems processes, we look at shift invariant measures, and some people talk about symbolic dynamics. The symbols are what in statistical mechanics you would call spin values, and they come somehow in two flavors. You can think of time, discrete time. If you think of all the integers z describing time, and you get a kind of asymmetric description because there is a big difference between the past and the future. And that is where the SRB theory comes from, the dynamical system point of view. And it describes typically non-equilibrium situations. And the other point of view is that we think Z as describing one-dimensional space. It comes from mathematical physics, and there is not much difference between left and right. So there is a kind of symmetric description, and that is the two-sided description, and it describes equilibrium situations. So the basic question I wanted to address is when are both descriptions equivalent and when are they not equivalent? So as a simple background, I will start with the Markov situation. The Markov situation is in some sense for short-sighted people because you don't look very far. You don't look very far in the past, and you don't look very far in space. So if you think here, I assume that most of you have come across Markov chains sometime. A Markov chain, in a Markov situation, you say that the future is independent of the past given the present. So it comes in probability, ergodic theory, dynamical systems, and you can think of the Markov ideology as a very ahistoric point of view. All history is bunk, as Henry Ford, the well-known proto-fascist, used to say. In China, their first emperor had also this point of view. He wanted to erase history and wanted to history start with himself. In space, the Markov property says that the inside is independent of the outside given the border. So basically, this is, as we see these days often enough, take control of your borders and you don't have to think about anything else on your outside. The Japanese were actually quite successful in this. They isolated the country for about 200 years. So the mathematical question I will look at is if you look at two-state Markov chains, which are time-like models, and I compare it with one-dimensional nearest neighbor Ising models, which is space-like. And of course, in Ireland, they're not very Markovian. They like their long history, and they don't like hard borders very much. So, mathematically, what am I doing? I look at probability measures on two symbols sequences. So the configuration space consists of infinite sequences of pluses and minuses. And it is a well-known theorem of already quite old. You can even find it on Wikipedia. And for a scholarly treatment enjoying this book, says that stationary Markov chains, which are the invariant Markov measures in histories, and nearest neighbor gift measures in dimension 1 are the same mathematical objects. And the theorem dates back to the 70s, and it was independently proven by Braskamp, who was a student of Buchenholz, just like myself and just like Tony, and at the same time by Spitzer. So this is about objects in infinite time or infinite space. And it says that the two-sided Markov property and the one-sided Markov property give rise to the same mathematical objects. So the question is, if we try to be more far-sighted than the Markovian, does the sameness remain true? And the first case is try to be as general as you can imagine. You look at arbitrary measures on infinite sequences, and the answer is a very strong no. There were examples in the 70s already, the Gurevich in Moscow and Ernst and Weiss in the West. They constructed examples which were one-sided random, but two-sided deterministic. So the one-sided entropy, the Kolmogorov-Sinai entropy, is positive, but because of the deterministic two-sided property, the two-sided entropy is 0. The one-sided tail is trivial, the two-sided tail contains everything. So the one-sided and the two-sided point of view were maximally different. So it shows that ergodic invariants are one-sided objects, and ergodic theory turns out to be a very one-sided theory. So if it is true in the very regular case and not true in the general case, what do? You kind of try to be moderately regular. And the intermediate case we looked at is the continuous quasi-local ergodic processes. So what if we change the independent Markov to a weakly dependent property, which also goes by the terms continuous or quasi-local or almost Markov, and an important contribution to this was due to Penicillin. And the question then becomes, does the sameness between one-sided and two-sided descriptions remain true? By assuming this continuity, we exclude the Gurevich and Ernst and Weiss examples because they're not continuous. And it is a question which has been studied by a number of people. I write here a list of people contributing, and the answers are that they are the same with some extra regularity conditions. And somehow the reason why people looked at this is this SRB theory of thermodynamic formalism, that people try to encode dynamical systems as one-dimensional statistical mechanical systems. So you start with a problem which Z describes time, and you map it to a model where you would describe space, and you want basically to talk about the same kind of thing. And if things are sufficiently regular, this is justified. But continuity itself turns out to be not sufficient. And the somewhat surprising result is that neither class constrains the other one. It's not the case that one-sided implies two-sided continuity or the other way. Neither contains the other. One direction was known since 2011 due to an example by Fernando Carlos and Maillard. And last year, the Singer Schlossman, we published another example, the so-called Schumann projection, which is the one-dimensional marginal with two-dimensional low-temperature Gibbs measure. And there was an earlier paper by Petros and Dorlas also about this. Then, in the other direction, which is this, we were somehow the first giving the counter example this time was with Pierluigi, Aernout, and LND. So these stochastic processes just continuously dependent on the past. They were rediscovered repeatedly, and because everyone thought they were first discovering it, they all gave them their own names. So the literature is kind of somewhat confusing because the term I use is G measures, which was introduced by my team, but they're also called chains of infinite order, or chains of complete connections, or uniform martingales, or random mark processes, or Dublin measures. Or what I kind of like as a name, STAM. Stochastic changes, unbounded matter. They were introduced, I think, the first time in the 30s by a Romanian group, Nicescu Mihok, and by Dublin and Fontaine. In the 50s, Harry studied them, Mike Keane studied them again in the 70s, and Karikov in the 90s. And basically, they are part of ergodic theory and probability theory. The spatial version, the Gibbs measure or Gibbs fields are almost random, almost Markov random fields, where they were also discovered independently, but as far as I know, only 2 times. One by Lugushin in Moscow, and one in the West by Redford and Rebel in the end of the 60s. So we look at the simplest case here with Ising spins, so 2 state variables on each side, I and Z. And then Gibbs measures can be divided with Z. And another warning in the literature, when people in statistical mechanics talk about Gibbs measures, and the people in the SRB world talk about Gibbs measures, they use different definitions. The definitions are not equivalent. I will use the statistical mechanics convention when I talk about Gibbs measures. This is just continuity. That's it. So, what do I call a Gibbs measure? If you look at an infinite graph, which here will be just Z, the configuration space is the space of sequences or arrays in G, and I look at the probability measures in the configuration space. And they're labeled by interactions. Interactions are collections of functions labeled by finite subsets. If lambda a volume is a large finite subset, the energy of in lambda is the sum of all the interaction terms such that they have a non-empty intersection with the volume. And the tau describes here the boundary condition, the omega describes the configuration in the volume. And we say that the measure is a Gibbs measure if the condition of probabilities of finite volume configurations given the outside is given by this expression. And it should be true for all configurations in the volume, all boundary conditions outside the volume, and all finite volumes. This is the definition of what we mean by a Gibbs measure. And it is basically a rigorous version of the expression that the measure is 1 over the partition functions, that's e to the minus the energy, the Gibbs canonical ensemble. So larger energy means exponentially smaller probability. And if you talk about nearest neighbor interactions, it means that the phi of x, the interaction terms are 0, except when x is a pair of neighboring sites or single sites. And the Gibbs measure for the nearest neighbor model satisfies the spatial marking property, the property of finding some omega from 1 to n, given the outside depends only on the side just to the left of the volume and the side just to the right. So conditioned on the border space at 0 and n plus 1, the inside and the outside are independent. That is the spatial marker property is a Gibbs measure. And the 2-state marker chain is again a measure on this same sequence space. And then it is defined by the time-like marker property. Here, if I look at the probability of finding some configuration omega from 1 to n, given an infinite path, it only depends on the tau at time 0. And I can describe a Markov chain there's a via a product of 2 by 2 transition matrices, stochastic matrices, non-zero energies. And like I said, there's a one-to-one connection between the two-state Markov chains, and nearest neighbor is in given measures. So you talks about the same objects in the probability and statistical mechanics. So I mentioned continuity, and what do I mean by continuity? Continuity is in the product topology, and it means that two sequences are close if they're equal on a large finite interval. And this topology is metrizable. You can make a metric by saying that the distance between two sequences is 2 to the minus n, where n is the side which is the closest to the origin, such that the two configurations are different. So if they are all the same till a large n, then this 2 to the minus n will be quite small, and the sequences will be close. So a function that is continuous, if it depends weakly on sites far away, and mostly on what happens not too far away, or not too long ago, if you think of C as time. And there is some uniformity, so it depends weakly whatever you condition, whatever past you condition on, or whatever outside the condition. And in processes, you say that the probability of finding sigma 0 equal omega 0 given the past is some continuous function g of omega of the past. And these things were studied since the 30s. When Dublin and the Romanians studied them. And Harris kind of claimed or suggested that continuity should imply uniqueness. And my team in the 70s pointed out that there was a mistake in the proof. You couldn't conclude this. And 20 years later, again, there were a counterexample were constructed by Breslin and Kanikov. It turns out it's possible to have a phase transition in these G measures. There is a G function, it's continuous, such that for the same G function, there are two invariant measures. This cannot happen. This one-dimensional Markov chain, one-dimensional Markov chains are unique. And like a one-dimensional statistical mechanics system with short phase interactions have no phase transition. And there is a sharper criterion on compared to the Kanikov in a paper by Berger, Hoffman, and Vicious. Somehow, between the time the preprint appeared and the time it appeared in the journal, there's a gap of 40 years. I asked one of the authors why, and they didn't give me a very clear answer. I don't know if the first referee rejected it, they put it back in the drawer, and then 10 years or more later thought maybe there is some interest, but somehow there's a kind of a usually large gap between the two. So continuity of conditional probability more or less corresponds to the summability of the interactions. Summability means that the sum of the interaction terms containing the origin should be finite. So this means that there is a continuous dependence on the outside, on what happens beyond the border. And quasi-locality, physically, it means something like no or not too much action at the distance. If you change something behind the moon, it should not have too much effect what happens on the Earth. And this continuity plus condition of non-nullness, it means that a finite change in an infinite system costs a finite amount of energy. That is somehow equivalent to being a given measure. you should have the finite energy condition plus continuity. And if a measure has that, then it is a given measure. And a given measure for such a summable interaction is continuous and satisfies the finite energy. This equivalence was proved at the same time in slightly different form by Kozlov and by Bain-Sullivan, and that the slightly different forms are not precisely equivalent, was analyzed in a paper by Pierluigi et al., which next to the theorem itself is kind of interesting because the two of the authors' addresses, one is in Israel, the other one is in Lebanon, which is not very usual collaboration. So these two conditions make it possible to kind of check if a measure is a Gibbs measure. And you can show that the various measures of physical interest can be shown to be non-Gibbs. And for me, this has been a major research topic over the years. And the first time I disproved the Gibbs property was when I was in Israel, and Tony Dorlas was here, and we wrote a paper together in 1987. And then in this paper, we looked at the sign field of a Maassen Gaussian, and that violated the non-nullness and turned out to be a non-Gibbs measure. So I have good memories of my scientific past in Dublin, even though it was shorter than a number of the other people here. So a short remark on the Sina-Reuel-Bowen theory. The Gibbs, according to Sina-Reuel-Bowen, is always one-dimensional. It is in some sense more general than what people usually do in the evolution than for Reuel, because people look at much more general configuration spaces. They look at subshifts instead of the full shift. So there are more versions for that. But it is usually less general because there are much more restrictive conditions on the interactions. The typical condition is that the sum of the finite times diameter should be finite. And this is a kind of strong first moment condition, but stronger than summability. Okay, so now back to continuity and summability. Our result was that that low temperature Gibbs measures for Dyson models are not G measures. So the Dyson models, like I said, they're long-range Ising models. They have ferromagnetic pair interactions. The interaction between two sites at I and J here is their distance to the power minus alpha, and the alpha here, which is interesting for us in this sense, is between 1 and 2, because in that case there can be a phase transition. Alpha is larger than 2, there's uniqueness and there's no phase transition. So the phase transition happens at low temperatures. Then there exist two different Gibbs measures for the same interactions. One which is positively magnetized, the mu plus, and one which is negatively magnetized, mu minus. And one can also show that microscopic interfaces don't exist, which is a kind of one-dimensional equivalent of a famous two-dimensional theorem by Eisenman and Higuchi and Pierre Taylor. And because it's a Gibbs measure for a summable interaction that is spatially continuous conditional probabilities. And like I mentioned before, but remember, it's impossible for Markov tensor fields to have always units. The phase transition really requires some long-range condition. And our proof says that Dyson Gibbs models are not G measures. We have we have a technical condition that the alpha should be larger than the alpha star, but that's probably just the technicality. And the proof has some requires some hard work, but luckily for us, the hard work we didn't have to do because the Ratelli group had done it. So our proof added some simple observations to their work, which is basically complicated clusters. So the input was a result of what interfaces for Dyson models by Cassandro Miro Pico. So basically what they did was they looked at an interval in which all the spins to the left are minus, all the spins to the right are plus, so they kind of devolution boundary conditions. And then they show that there is a kind of fluctuating interface, an interface point, such that to the left of this point we are in the minus phase, to the right of the interface point we are in the plus phase, and the kind of most important thing is that the interface point is not localized, but it is mesoscopically localized. It is not too far from the center of the interval. If the interval is L, the typical distance is at most L to the power alpha over 2 to the center. And because alpha is between 1 and 2, that is except for alpha is 2, it means it is much closer to the center than to the boundary. So you have all minuses as a boundary, then you have a minus m, then you have the interface point, then you have a plus m, plus positively magnetized interval, and then you have the plus boundary. So this is the typical situation if you take the devolution boundary conditions at an interval of size 2. So the first observation is if I take a huge interval of size n, much larger than the interval I'm looking at, and I change all the spins of that L interval, the effect of my change on the central interval is small, because it's bounded by the length of this interval L and the distance where I make the change, which is n. So the n to the minus alpha, I really take a summation because the n to the 1 minus alpha is bigger than 1. So if I take n large enough, this is a small number. So it means that there is not much difference if I take minus everywhere to the left or minuses all the way to minus n to the left. My interface point will still be more or less in the same interval in the middle of my interval. So what does it mean? If I insert a large interval of minuses somewhere, then there will be a moderately large size L interval minus phase on both sides. It means physically that the interface is pushed away. So we have some form of entropic repulsion. The second observation is if I decouple a relatively small but still diverging interval of size L1, small of L, inside the beginning of my minus interval, this hardly changes the interface location, because the cost of shifting the interval by something proportional to L is of the order L to the 2 minus alpha, and this is larger than my L1. And this the cost of the shift was shown by the Sandro. And the third observation is if this interval I don't decouple, but I make it an alternating configuration, then the total energy here of this alternating configuration is still relatively small. I have a double sum, it's because it's a double sum of things for j minus I minus j minus I plus 1. So this is basically you gain an extra power, or you lose an extra power, and it means that instead of something which a priori could be divergent, now I get a convergent sum, which is bounded uniformly in this alternating cycle. So it's a small effect, and again, it doesn't change that much the size of my interface. So if I take a very large interval of minuses, and then an alternating interval, I see basically the same as having all minuses. So this is typically a non-zero temperature effect, which is due to this entropic repulsion, which is not a thing which happens at zero temperature. But what does it mean? It means that if I take a large interval, alternating interval, preceded by a much larger interval of minuses, it's this alternating interval cannot shield the influence of this homogeneous interval. But continuity would say that if I have a large alternating interval, it should shield the influence or what happens beyond this alternating interval should get small, but it doesn't get small. So because it doesn't get small, it means that there is one-sided discontinuity. So we have two-sided continuity because we had a Gibbs method for summable interaction, and we know from Ben Sullivan, for example, that we have continuity, but at the same time we have a one-sided discontinuity. So there are also examples in the opposite. So it means that one-sided and two-sided continuity they have a large intersection, but they are really different masses. This alternating configuration is a discontinuity point, and such discontinuity points they may have measure 0, but you can't get rid of them by redefining. So we have a direct influence from the deep past, which is kind of not allowed in if you would have continuity. Okay, so this was the first result I wanted to talk about. The second question comes from an observation which we get if we look at the interaction between two half-lives. If we call W the sum of all interaction terms from the left half-line and the right half-line, then it is true that its expectation is finite at high temperature. If you take two random half-lines, either independent or weakly dependent, then weakly dependent at high temperature, we know that the correlation decays at the same rate as the interaction. So the expectation of the product of two spins is O to the I minus j minus alpha. So if you multiply that with the interaction term, it's also goes like eta minus alpha, you get I minus j to the minus 2 alpha. And 2 alpha is larger than 2, and then the sum of this double sum becomes finite. On the other hand, the expectation of the W at low temperature between the ordered half-lives, say between everything all plus, is infinite. That is actually the reason why phase transition can take place. If the total interaction between left and right half-lives would be finite, there's no phase transition. If the interaction can be infinite, we can have a phase transition. But the new observation we made is that if you take a random half-line on the left, so you take IRD plus or minus 1, and ordered plus half-line on the right, the interaction energy is finite if alpha is larger than 3/2, and infinite otherwise. The reason is you take the sum of the eta I plus or minus 1 times a term which is essentially the distance of the I to the origin to the power 1 minus alpha, because it's you have taken 1 on summation. If you then take the sum of these random terms, basically by a kind of central limit theorem, if you take a sum of n terms, you gain a term not of n, but the square root of n. So you get, instead of 1 minus alpha, you get the 3 half minus alpha. Basically, it is a central limit theorem for non-identical independent variables. And that's the argument for independent, for high temperature. Well, what I mean when I talk about random, it doesn't mean independent, but weakly dependent. But weakly dependent and independent behave the same. And you have to do some work for that, and I prove we use a tool which is called concentration. But the underlying idea is that weakly dependent behaves like independent. And the underlying idea is correct. It can be proven, but the proof doesn't tell you more about the information. So the consequence, there's two consequences which somehow are quite different. One is at low temperature and also at 0 temperature. If you look at a system with random boundary conditions, then if alpha is less than 3/2, we have two limit points, the plus measure and the minus measure, and we need some condition about taking sparse sequences. And that is similar to what happens in higher dimensional behavior. In terms of what is called the Newman-Stein metastate, it lives on the two pure states. On the other hand, if alpha is larger than 3/2, we always get mixed states, because the boundary energies typically don't diverge. This is somehow unusual in situations of phase transitions. Usually boundary conditions tend to select pure states. This is an example where they don't. These random boundary conditions, even though they are not like symmetry, like free or periodic, but typically we get different mixed states as limits. The limit distribution on the possible limit state is called the random state. So it's either supported on two pure states, the plus or minus, or it is some probability distributions on all the mixed states. So it's a probability distribution on the weights in the measures. So this metastate is kind of a measure on measures, measure on given measures. And the second consequence is not a low temperature, but a high temperature. And it shows that at the half line, random equilibrium density between the free boundary condition, half line given measure mu, and the marginal characterization invariant Hodam given measure is continuous, and alpha is 3/2. There was another proof found by Johansson, Oberg, and Polycott. And it is non-continuous, it's unbounded if alpha is smaller than 3/2. And somewhat surprisingly, the whole line counterpart, if you take the random equilibrium derivative between the product of the two half lines and the whole line, it's always L1 but not continuous. And basically, formally, you write you compare the given measure for the left and a half, left and right Hamiltonian versus the translation invariant one. The random equilibrium derivative is e to the w. It's integral at high temperature, but unbounded. But if you integrate it over a half line, it becomes bounded. You have tried to think if you could do something at higher dimensions. An analogy of the G measure property is Could be something like the global market property. Then you condition on infinite volume like half-life events, but it's known that there are market fields which are not globally marked. And there are also market fields which depend discontinuously on electrical traffic patterns. So somehow, yeah, you can't really you do that much in higher dimensions. So the conclusions is that two-sided continuous dependence does not by one-sided continuous dependence, but neither is it implied. So controlling borders is not the same as controlling history, except if you're short-sighted. The second conclusion is that if you restrict to a half bind, you can smoothen relativity derivative. And the third thing is that random boundary conditions in the phase conditions may not be able to select pure phases. So I wrote some papers which we wrote down some of the things I was talking about, and Mahmoudov wrote some extensions to what happens in the not very high, but all supercritical temperatures, and also what happens in an external field. And there are other things you can do about the Dyson models. You can do, and there are some questions here. This technical restriction on alpha is open. Either what happens in the alpha S2 case is open because then the interface point fluctuates all the way in the whole interval. So then our proof takes down. We have done something about metastability, and we wrote that it's universal with Spitoni, and we improved some technicalities with Kimura, with student of us. And there is a similar, an independent work written about adding external fields. So this is the end of the talk.
So the next final talk today is by Pierluigi Contucci, statistical mechanics and artificial intelligence. So thank you very much. The last speaker of the day has the responsibility to keep the audience awake. So it's a tough one because the day has been long. And first of all, I want to thank the Institute and for the invitation, and a very happy birthday to I was visiting here in 2010, and we had very nice talks, which had some statistical mechanics, the Sherrington-Kirkpatrick model, large deviations. I remember that was very nice. Okay, I'm going to give a non-technical talk, which is even more suitable at this time of the day, after many seminars, but of course I'm available to technical questions. And somehow I'm going to explain what statistical mechanics has done, and very likely is going to do for AI, for artificial intelligence. The way I start this seminar that I gave somewhere is challenging the audience to say who wrote this sentence, which is a very reasonable sentence. You can read it. Despite refinements achieved by intelligent machines, their theory is sparsely developed. The attempt to improve their techniques is still conducted heuristically. The generation of knowledge from data has yet to be addressed from a truly general standpoint. No. AI is it's an answer that I get often. The truth is that I did, but the blue
the blue things, and the entire phrase is a transliteration of this. Have a look at. So I believe that this similarity is very profound, and most of my talk will turn around this similarity. So what happened when the steam engine was invented? Let's say the first steam engine that were really producing work out of coal or wood were already working quite strongly, quite fine in 1780, right? But this statement is by Sadi Carnot. It's in his book, Réflexions sur la puissance motrice de feu. It's 1824. That's the date of birth, another date of birth, Tommy. This was the date of birth of thermodynamics, basically, because the second principle of thermodynamics was invented by Carnot. And by the way, the first explicit formulation of the first principle of thermodynamics comes much later, in 1842, if I'm not mistaken. Okay, so 18 years later. Although in this work by Carnot, it is already implicitly assumed that something like the conservation of energy is taking place inside the machine. So we owe to Sadi Carnot the entire corpus of thermodynamics. So I want to comment a bit and stay with this historical comment for a while. What science did we have at those times? Well, mechanics was very well developed because Lagrange, okay, don't remember the date of birth of Lagrange, but I remember the first lecture at École Normale. So it was in 1795, first lecture at École Normale, and Lagrange was 51. Mechanics was done with the Lagrangian formalism was already there. So mechanics has reached the level of science, real level of science. All the theorems in mechanics could be derived from the Lagrangian formulation. That was a very general, very powerful, still is taught in school, well, at the university, somewhere actually. Classical mechanics, at least in my university, is a fundamental class in mathematics. Why am I observing this? Because the invention of the steam engine was based strongly on mechanics, also on Lagrangian mechanics, okay? And then there were a few additions of a few concepts of, let's say, calorimetry, thermometry, okay? At those times, thermometry was measured in centimeters. You might know that. There were no Kelvins, no whatever. It was measured heuristically and empirically. And also the concept of heat was still very vague. So with the arrival of the steam engine, what happened was that a new technology that became the focus, the basis of the Industrial Revolution, made a jump ahead so long that it landed with an object that was not understood anymore. So the steam engine, when it started to work, when it transformed the United Kingdom into a worldwide power, was not something that scientists could explain. So the steam engine, in fact, is called by someone. I had these long conversations with Lucio Russo, an historian of science, and by the way, an excellent, Aernout probably knows the work of Lucio Russo.
Russo Seymour Welsh.
Exactly, Russo Seymour Welsh. Well, Lucio Russo spent years of his life with history of science, and with him, discussing, we We call that the technology of the steam engine a pre-scientific technology, which is based on science, mechanics, but it makes a jump that is so long that science doesn't know anymore how it works. In fact, thermodynamics arrived 40 years later. The second principle, and the first principle, the idea of the conservation of energy, it arrived 18 years after the second principle. So why am I saying that? Because we see many similarities with what is going on right now. So what is artificial intelligence today? It's based on of course, many pieces of science. Should we mention some? How does it work? Artificial intelligence in the deep networks that produces all the wonders that we play with. Everybody here is playing with ChatGPT, right? We know, all of us, yeah. Okay. So what is it based on? Well, computers are made with chips. Chips have transistors. Transistors have physical basis that is quantum mechanics, but the computer that we use is not a quantum computer because the transistor acts like a classical device. The computer runs on electricity, so the entire Maxwell theory, Maxwell equations are working there, and much more. Miniaturization, microelectronics, etc. At the same time, the artificial intelligence nowadays is not understood. So artificial intelligence is as much as the steam engine, pre-scientific technology. So it started with scientific means, like those that I mentioned, quantum, electricity, and so on. And it's making a jump that is so long that science is not able to get to what do I mean? Science has not reached it yet. I mean that we don't know what are the principles on which those machines are working. Of course, there are people trying to understand deeply how this machine works, but I would say, I don't know, Nicholas, how much can people work in things related to AI be from the interpretation, from the scientific point of view? Less than 1,000 in the world? It's an estimate, you don't know. I think they are less than 1,000. Perhaps 500 people. Well, at those times there was Carnot alone, so we are lucky. Okay. So that's my first observation.
So you're looking for some kind of global concepts that describe
new concepts that are able to tell you why a machine, an intelligent machine built by OpenAI works better than another with the same database, because there are differences of that type. The steam engine, there are documented facts that steam engines were compared from the efficiency point of view. But when you ask the guy who built the steam engine in Berlin or the guy in Paris, they did not know why one was working better than another. Actually, I was saying I was reading newspapers of those time kept in archives, and they say it's a matter of lubricants and stuff like that. Instead, it was not. The leading factors were the two temperatures, one inside the chamber, and the other is the temperature of the environment, among other factors, of course. Why? Because the second principle of thermodynamics had not been discovered. Okay? So the same thing is happening now, and in fact, Ian LeCun often claimed that what we need now is a thermodynamic theory of learning. Okay, and the last word I'm going to say about this slide is that it's thermodynamic theory of artificial learning. That is what Ian LeCun called the high-level research in artificial intelligence. We need a thermodynamic theory for learning. Learning is transforming data into knowledge. By the way, those are words that have to be explained, but the data are pictures of cats and dogs. The knowledge is the ability to recognize among those two animals, one ability that we take for granted, but that now even machines have, actually in superhuman level. Okay. So this whole business with artificial intelligence works with a very simple elaboration of data, that is the artificial neuron, applied, of course, 10 to the many powers times to data and properly addressed. But let me explain, if you've never seen, I apologize with those who have already seen this stuff, but let me mention. So what is an artificial neuron? It is a sort of mathematical, very simple, very crude mathematical description of how a neuron works, because this artificial intelligence is based on the imitation of the functioning of the brain. So there are data that we call inputs, like this one. There are parameters that connect, are associated to those black links. So those x1, x2 up to xn are mixed with these parameters. This is a simple multiplication of a matrix. And then there is another parameter, dk. So this sum here plus the b, by the way, the w are called weights and the b are called biases. You sum in I from 1 to n, and then you compute a nonlinear function of this green box, and your output yk is just the computation of phi of this quantity here. What does it stand for? Well, it simply says that what the neuron, an artificial neuron, does is to elaborate the inputs and fire a signal after that. That is the function phi. Function phi, you can choose your favorite, even non-bounded, nonlinear function. From statistical mechanics, I like the hyperbolic tangent that was used at the very beginning in this kind of artificial neuron, but now there are other functions that are used into large machines. Actually, if I compute the hyperbolic tangent of this expression here, and I say that yk is equal to the hyperbolic tangent of this quantity, that equation is connected to what Aernout was talking a moment ago, because it's the DLR condition of an Ising spin, okay? Condition on the nearest neighbors in the mean field approximation, because instead of the spins, I have to compute their magnetization. So those xi and yk are the magnetization.
So the inputs are the same shape changes?
No. The inputs are inputs. So x1, x2, xn are the data that you feed into the
data is collected by
the data is a box that you have collected earlier. And you have to. Okay, so this concept, the artificial neuron, was sort of not in this form, but was this concept inspired by work by McCulloch and Pitts in 1943. And then a few years later, a bit more than a decade later, 15 years ago later, Rosenblatt in 1958 proposed a series of those artificial neurons that should have very, very nice properties. In which sense? It was supposed to approximate every function. You start from data, you want to obtain some outputs, and you ask yourself, can I find W and B in such a way that this function represents a function that I choose? Okay? So there was a negative answer to this question. So this approximating perception was not able to describe every function. And these two people made an example, found a counterexample that is the XOR function in computer science. In set theory, this is the symmetric difference. Okay?
But for this question, were they able to choose any arbitrary nonlinear function for phi? For this Rosenblatt, for the question if the perception of the Rosenblatt.
You can choose any arbitrary function phi, and there are counterexamples, and you cannot reproduce.
Even if you have the freedom.
Yes, even if you have the freedom. And actually, it's a very simple observation that has nothing to do with modern computer science. It's a known fact that function like that cannot cover the entire set of functions. But it was later observed that if you just iterate once this map, so if instead of doing it once, you keep doing this map between more layers of neuron, that's not true anymore.
So it's a mathematical fact that
It's a mathematical
the
fact.
combination of affine transformation and a nonlinear function cannot give you any arbitrary function, but if you just are allowed to iterate it once, then you get the whole.
Then you get an approximation of all the functions you want. Yes, and it's a very simple theorem, by the way, and it's well, I could explain it, but I can do it later.
It did not.
Okay, what happened after that? There was a long period in which the perceptron was announced in the New York Times as something that could really learn data and functions. And the announcement was somehow spectacular, saying that these machines will be able to translate, to help with computer vision, etc. But nothing like that happened. And the reason, as it was understood later, was that those machines, from the technical point of view, were not strong enough, were not fast enough. So the scale was not good. But the idea, after Minsky and Papert in '69, didn't change much. So what happened after that was the introduction of deep neural networks. So this symbol here is one of those modern deep neural networks, and those arrows, those links between nodes represent the same operation. On the left, I put my database. Here there is X1, X2, etc. I propagate forward the signal that comes from my database until I compute the what comes out in this last layer of neurons. To be more specific, imagine that you have a database. This is also to answer the Joe question. A database is cats and dogs. So you take one picture of a cat. The picture is digitalized. You can imagine as zeros and one, if you like. The picture is black and white, or also in general. You put the picture on the first layer, okay? And then you have to codify your answers. So you call cat the code 01 and dog the code 10. You propagate the picture of a cat from here to his label, that is 01, and then what you do, you adjust all the weights W and the bias B until the map coincides as good as possible with the label at the end. I don't know if I'm clear enough on this explanation. So you propagate feed forward in this network the signal that comes from there, and if what you get at the end is different than what your classification that you have decided arbitrarily 01 for cat, 10 for dog, you go back and wiggle those ways W and B until they coincide, and you repeat for many pictures of cats and dogs.
Are there not too many parameters to all change?
The question is, aren't there too many parameters?
Yes.
Yeah, there are too many parameters, and And that's the point. I come to the question. So you decide what is the distance between the outputs and your classification, which is the code that you decide. And how do you identify the parameters? Well, there is this method that is called backpropagation and the stochastic gradient descent. You go back and you change, you wiggle until the two, what is expected and what you got coincide. And you repeat it many times. Of course, this is a sort of cartoon picture that I'm giving, but the algorithms that make this work are very plain and simple. The point is that we do not have idea on why they work so well. Why am I saying that? What do they do? Okay, the search of the optimal parameters, as I write here, is a search in a very wide space. The W's are very many. For instance, the W's nobody knows how many ways there are in ChatGPT, but they are of the order 10 to the 13. Okay, 10 to the 13. And in order to do that computation, you need a lot of power, you need a lot of energy, and also a lot of time, and many data. But let me go to some features of this search. It's a very high-dimensional search. The objective function is loss function, the difference between what you get when the machine is not trained and what you want to get is highly non-convex. So you are trying to go down in a multi-valleyed landscape and search for the minimum. It's not a parabola, this landscape. It's really highly non-convex. So why does it work so well, and what is the observed behavior? So first of all, when I don't know if you have ever worked with a high-dimensional inference, if you're trying to approximate a set of points with a function, for instance, okay? Well, if the points are in a line, that's very simple to approximate. But if the points are not, you always find a function, arbitrarily complicated function that approximates all of them. But this function has the danger of overfitting the data. Because if your aim is to generalize, that's a key word in artificial intelligence. If you really want to generalize your database, which means you have trained your machine with a database that contains 1,000 pictures, and now you show to the machine a new picture that the machine has never seen. This type of artificial intelligence has generalized it. It recognizes a cat and a dog better than you do. It distinguishes races among of cats and dogs, and it does things that we really are superhuman. It beats you if you play Go. It overbeats you if you play chess. There is no chance, no one is beating AI anymore in chess. There is really, I don't know if you play chess, there is this, what is called Elo score, that the machine is order of magnitudes ahead of us. Okay? So it does not suffer the overfitting phenomenon, which is typical of high inference. Instead, he has this strange phenomenon of the double descent phenomenon. And what is it? The generalization error in standard inference. It goes down when you increase the number of parameters. And then it doesn't improve anymore. Actually, it goes up and it stays there. Within these machines, instead, it goes up. But if you have resources and you increase again the number of parameters, it goes down. And that's called double descent. Double descent phenomenon is not understood yet in deep network.
So this is just empirical observation.
These are empirical observations. So these machines have optimization, optimal generalization abilities. And there is also, this is an important fact, performance improves if you keep adding parameters. So there came out papers in 2018, and these papers are called scale laws or something like that. What do they say? Well, if you try to train a large language models with data and more parameters, it seems that the performance of the machine is not bounded as far as in the range that it has been observed. Because there is an improvement. This machine keep improving with the number of parameters. This observation was made in 2020. Two independent teams discovered that this performance is increasing. And for that reason, rumors say, for that reasons, so groups like OpenAI are investing tons of money with this technology because they want to build huge machinery, much bigger than those that we have. In fact, OpenAI through Microsoft has bought the nuclear power in the United States. 3 Mile Island is now belonging of Microsoft that will reignite the nuclear power production.
But it's all based on conjecture.
Well, that's a good point. It's based on a bet.
Yeah, it's a bet, but there's no mathematical proof that the scaling...
Here there is no mathematics. There are empirical data and there are scaling laws, and scaling laws are not theorems, and so
No,
definitely is no mathematical proofs. What are the real results that we have? There are nice works that say that why does that algorithm converge at all? Because these minima in this complex landscape are wide and flat. It's a very qualitative description of the situation. These are high entropy minima. So wide and flat, so it's easy to reach them from many directions. It's not that you have to find the whole of a golf field, okay? So these are results that I know a bit better, especially because one of the authors is Riccardo Zecchina in Italy. And there is also a very nice mathematical work by Andrea Montanari, who sort of understood this double descent phenomena, but in very simple model, not in the deep network. So as Giorgio Parisi often says, the figure of Giorgio Parisi will appear very soon. We understand quite well the perceptron, the original machines that cannot generalize very well. We understand the shallow networks that are 3 layers, neural networks. But as far as multi-layer neural networks, that these here, we know nothing. There is no clue on why they work so well. And these artificial intelligence, deep network and transformers that are an evolution, special use in large language model of deep networks, are by far pre-scientific technology. They have been built on science, but jumped very far, and we do not understand anymore. Okay, so these are other observations, 3 observations that I'm going to make. In order to get this intelligent behavior, we need many neurons, for sure, and organized according to that architecture. For instance, if I make a very tall neural network and not deep, it doesn't work. I mean, the iteration, the successive iteration of the neural network is a very important element. So I need many neurons in a very specific architecture. It's also interesting to see that the machine itself is trained by a very hard procedure to identify the W's, those parameters. When the neurons instead can have a different behavior inside the machine, because when it is used after being trained, the neurons have a very fast dynamics. You raise a question to the machine and it answers immediately. So the behavior of the neurons in a way is very quick, but the determination of the coupling constants, those constants, is very slow. So if you observe the functioning of the machines, there are two time scales here at work. And another extremely important fact is that these synaptic parameters that I mentioned have alternating signs. And this reflects the fact that the artificial brain is imitating the brains, the biological brains. Some synapses are inhibitory and some synapses are excitatory ones. Okay, so it's not an amplifier brain. If you, for instance, impose the machine to have only excitatory synapses, it's not working as a brain, it works as an amplifier. Okay, so these are three things that have some importance. Let me come to the point. So clearly, theoretical physicists raise this type of question. Is it possible to understand what is going on under a scientific scheme? Something that says, okay, there is this principle, okay? And the machine is working in all those cases according to this principle. For the moment, there is nothing like that. Yet, it's clear that statistical mechanics or some form, here there is optimism and the vice versa toward the use of statistical physics and statistical mechanics. It could be an answer, it could not be an answer, but some type of statistical physics and statistical mechanics should be able to give some answer, because for an artificial machine like that to work, it needs a very large set of neurons and a very, very large set of parameters like those W's. And what is the view, the general view behind those ideas in statistical mechanics? The fact is that this box of the deep network can be seen as a system of interacting particles. Okay, we don't know how those particles interact exactly, but the idea, the proto idea, is that these are a set of interacting particles. The labeled data set, which is the data set of the pictures on the left, and the data set of the labels, somehow work as boundary conditions. Okay? So imagine your Ising model to be very, very simple and try to answer the inverse problem that tells you, okay, suppose you want to impose a set of boundary conditions, but not one, as we are accustomed to. Many boundary conditions in average. What is the set of coupling constant and magnetic fields that better make these boundary conditions work for the machine? This is one of the ideas that are going around in AI. And so the feed-forward map that I try to describe the backpropagation, that is the algorithm with which you compute those parameters. And this acronym is stochastic gradient descent, which is the way of finding minima in this multi-valid landscape, are techniques to approximate, this word here is used improperly, local equilibrium, some sort of equilibrium that we don't know. Now, what has statistical mechanics done for this task? Was it useful? Why am I claiming that there is some intersection between these two, between this pre-scientific technology and statistical mechanics? Let me also comment on this. After training a machine, you discover, as I said, that the W's have alternating signs. So it's not a ferromagnetic system. Okay, it structurally contains interaction that keep the two neurons behave alike, or some of them behave as in opposite fashion. So if there is statistical mechanics here, it's going to be a statistical mechanics of the type spin glass, disordered, and the like. Okay, why physicists enter the game very late in this sort of, because this is the period of time in which physicists started really to be interested in artificial intelligence and neural network. This is an important point too. And why they started with cybernetics. Okay, the Hopfield model comes out in 1982. This is the date of birth of, how much time do I have? Is it, am I done?
You started around 4:40.
Something like, it was past 30. Okay, thank you. So the Hopfield model was proposed in 1982. The Boltzmann machine by Hinton and Sejnowski, which is the interpretation that I mentioned. The Boltzmann machine is basically saying there are particles, they interact, there is an energy function, perhaps what artificial intelligence does is it's trying to realize some sort of equilibrium measure, okay, through an inverse problem for fixed boundary condition, for an ensemble of boundary conditions. The Boltzmann machine in 83. Okay, my first observation, which I think has some relevance here, is that all these Boltzmann machine Hopfield model would have been unthinkable before the work by Giorgio Parisi. Why am I saying that? Because before the solution of the Sherrington-Kirkpatrick model, there was no way one could figure out what are the properties of a system in which you have mixed ferromagnetic and anti-ferromagnetic interaction. There was no clue. It was, of course, a model that you could consider, but it was impossible to have any idea on what it produced, what is the equilibrium state. So it was the work by Giorgio Parisi who strongly influenced not only this network here, the Hopfield model, that is not a learning model, it's a model for the associative memory, but that nowadays has a larger and larger importance also in the study of learning, so in the study of deep networks. And in particular, all these ideas sort of boomed after this meeting that took place in 1985 in Les Houches, Disordered System and Biological Organizations. Among the participants there were Hopfield himself, Mézard, Virosor, Ian LeCun. And the funny thing is that everybody that I talked to, participating to that meeting, is convinced that Giorgio Parisi was there, but he denies that. He was not there, but everybody was talking about the solution of the Sherrington and Kirkpatrick. That was the main discussion in this meeting. And most of the things that have been said there was also Hinton, I believe. Hinton was there, one of the Turing Medal awards for AI, and now Nobel Prize for Physics. So statistical mechanics somehow entered the neural network and the learning production after Giorgio Parisi solved the Sherrington and Kirkpatrick model. Because before we had no, they had, I was still very, as a kid at that time, more or less. No, in 85, I entered the university. But there was no, before Giorgio Parisi, there was no idea on how to deal with a system of interacting particles in which you have mixed ferromagnetic and anti-ferromagnetic parts. So the Boltzmann machine is I'm going to describe a bit what is the Boltzmann machine. It's defined by an energy function on a set of interacting variables, ds, that represent the status of a neuron. You can think of them as real numbers or Ising spins. The W are usually called J, and the D's are called H in our field, but the energy function is what it is. And then in a Boltzmann machine, there are visible units where the data set is assigned. This is a bit of terminology. And the hidden units that instead are left free. In the architecture that I've shown to you before, the visible units are the boundary condition, and the hidden one are those in the middle. So the system is trained with the visible units, the boundaries, and what the training does is to compute what are the W's and the This is a high-dimensional statistical inference problem in W and D, and the special architecture that I've shown to you is also called restricted deep Boltzmann machines. If you do a bit of computation in this case, you see that you have a data set. If I indicate with this symbol here the empirical mean in the data set, okay? So it's just the empirical mean that is you average over your data set. To each configuration of neurons, some of them are visible, some of them are hidden, you associate the restricted Boltzmann machine measure. That's the Gibbs measure. And also the conditional measure, the conditional Gibbs measure on the visible units. Okay, now you are left with for instance, maximum likelihood problem of inference, and the condition that guarantees to you that the W do their job as best as possible is that when you have some observable of visible units and hidden units, this average here, that first average the hidden units with the conditional Gibbs measure on the visible units and compute the product with other observable of the visible units is equal to the global Gibbs measure. How can you make those two to be as close as possible? Well, there are algorithms that wiggle again those W's and those B until that two quantities get as close as possible. This set of algorithms are called contrastive divergence. The problem with this approach has gotten better over the years, and now is not used by the large industries, but it's still very considered among scientists. It's difficult because the Boltzmann average must be sampled if you have no good knowledge from the theoretical point of view. So what kind of measure is this? The Gibbs measure of an energy like that. In general, we don't know their properties, right? So we don't know how to solve what is the free energy of a Boltzmann machine. So this method here suffer of this drawback that must be sampled. So you have to compute it numerically. What are their properties? Instead, if you would have an exactly solvable Boltzmann machine, that would give you an enormous advantage to understand what is going on with that technology. For this reason, we have we thought that we tried several toy models that I will shortly report here in my work. I have in Bologna. So, what is the idea? We assume that the data set is generated by some underlying probability distribution. So these Boltzmann machines map this probability, assumed probability distribution that has generated the pictures of cats and dogs, and the training of the Boltzmann machines map that distribution of data into a probability distribution of W's and B's. Another thing that has to be said, when you train a machine, the solution of W's and B's is not unique. You have an ensemble of solutions that works as well as any other. And now, what are the fundamental properties of this statistical mechanics model? The free energy, the phase space, are they analytically solvable Boltzmann machines? Those are problems that we have considered, and we have invented, invented the simplest Boltzmann machine that, of course, is based on properties of the distribution of the W's and the B's that are absolutely elementary. So how does it work? The Boltzmann machine with W's and B's that are Gaussian. What is the property of a restricted Boltzmann machine in which you have Gaussian? So you have these layers of spins. Interact interlayer. Right? So every layer is connected to every layer, nearest neighbor layer, all of them, but the spins are forbidden to interact within the same layer. Okay? So what is the simplest model that we could come up with? The story is very frustrating on one side, because not even the simpler model we are able to solve. And why is that? Because the technique that has been used to solve the Sherrington-Kirkpatrick model, that was hopefully the best that we could do in this case, fails for an architecture like the one that we have. Let me explain to you why it fails. Okay, what is is really a very quick story of the SK model. That is the model probably that I spent most part of my academic life with. So the model, the SK model, is the simplest model of spin glasses, sort of among the simplest model of spin glasses. The J, and the H are Gaussian, IID Gaussians. The model is fully identified by this function here, to the square power, where Q is the overlap. It looks like as you see, it looks like a magnetization, but of two different sets of spins. And one of the features of this model is that the overlap has intrinsic fluctuation in the thermodynamic limit. It's not like the magnetization in the Curie-Weiss model that is almost always concentrating to a point, apart from the critical line where there is the phase transition. In the SK model, certainly there are parts of the phase space where the cumulative function is concentrated on a single point. But, so this is a correct picture of high temperature and magnetic field. But if you lower the temperature and the magnetic field, you find situations like this that could still be classical in a way, because there are other models with several equilibria, okay? Pirogov Sinai or whatever is your favorite one. But what happened in this case is that if you keep lowering the temperature, something like that appears. A continuous distribution for the overlap function. Okay, this is a totally new fact with respect to classical statistical mechanics, and it's also the main reason for which Parisi was awarded the Nobel Prize in Physics in 2021 for this solution. The solution proposed in 1982 became a rigorous corpus after, again, 30 years or more of investigation, especially thanks to Francesco Guerra, Michel Talleyrand, that was awarded to this prize, and also Panchenko, Dmitry Panchenko, who worked out the proof of the so-called ultrametricity property. So how is it expressed, the solution for the Shannon-Kirkpatrick model? Through a variational principle, which is not an ordinary variational principle like for the Curie-Weiss model, where you optimize with a number. What is the magnetization that solves the Curie-Weiss, the ferromagnet? Here, what you optimize on is a function, this distribution, cumulative distribution of the overlap, and that's the functional that is involved. But the nice thing about this equation is that in spite of the fact that the energy is a multivalent landscape in which you have maxima and minima, and as soon as you change your spin configuration, you go up and down, this variational principle instead is a convex problem. So you solve this problem here, which is the solution of SK, by simply computing the function x in a convex space. This was proved by Chen in 2015, I believe. So this is a very quick crash course in the structure of the Shannon-Kirkpatrick model to tell you that in spite of the fact that there are ferromagnetic and anti-ferromagnetic interaction, it's still possible to get the solution with an optimization procedure that is a convex optimization procedure. We had hoped that a more complicated model, but still a toy model, could obey to a similar variational principle. Instead, what we found is the following fact. We studied in the last 5 to 10 years generalization of the Shannon-Kirkpatrick model, in which it's not that every spin is interacting with every other spin, but the spin of a layer interact only with the spin of the next layer, and the next layer, and the next layer, and the next. So what we have done, we have broken the permutation symmetry of the Shannon-Kirkpatrick model, okay? And moreover, we left the freedom to choose all the J's in this layer to be IID, and the J's on the second layer to be different IID, and so on. And also, we decided to leave as 3 parameters, alpha 1, the number of spin, the percentage of spin in the first layer, the percentage of spin in the second layer, and the percentage of spin in the last layer. That is, these are called the multi-species model that we have worked with for a while, myself, the people in Bologna, Dmitry Panchenko, who considered these models among his favorite StatMech model. And the point is that there are cases that we can solve and cases that we cannot, unfortunately. the deep networks are unsolvable so far. Why is that? Because to identify the solution, we need a strong interaction among the spin in the same layer, which is strictly forbidden by the deep architecture that are used in artificial intelligence. In fact, the interaction within a layer is totally forbidden in the deep network. Why is that? Why is it costing us the inability to identify the solution? Because imposing, forbidding the interaction within the same layer make us lose the so-called positivity property that has been discovered by Francesco Guerra, which is at the origin of all the rigorous results in the Sherrington and Kirkpatrick model. So we know how to solve multi-species model only if we allow the interaction within the same layer to be on and to be strong with respect to the out layer interaction. So we got nothing? No, actually we got something, and this is the final part of my talk, because we were able to solve the easiest part of the model, which is the high temperature phase of the model. So what we found was that the high temperature phase, which is of course a complicated, not a complicated, it has to depend on all those parameters, alpha, k, but also on the variances, on the empirical, on the variances of each layer. The j here have a variance that we call delta 1, the j there, we call it delta 2, and delta k, -1. So those are our parameters. We were only able to compute the free energy, the pressure of this model in the phase space where the system is just a second, where the system is, well, where the system is, the average of the logarithm is equal to the logarithm of the partition function. So it's the so-called high temperature regime for these models. What did we get? A condition that looked like a boundary in the phase space, where the model certainly cannot be an intelligent system. So why is this condition produce some nice results? Well, this is the work that I'm talking about, that will finish my talk. The phase is called the annealed phase. So controlling the annealed phase is only controlling the high temperature regime of the model. But we were able to impose a condition that would compress the annealed phase, make it as small as possible. With this condition, we have used this condition experimentally in training a machine. And what came out is that this theoretical condition that would make the annealed phase as small as possible produced some improvement with respect to the real machines that we tested. So our test was very small. The database was extremely, one of the initial database that people have used is called the MNIST. It has only the numbers, so it's a database that was originally used by Ian LeCun to read the post code in the United States. So we make this test, and what we found is that even the knowledge of the annealed phase, which is the high temperature, the request of making it as small as possible, that turned out to be a very simple condition, is able to improve the robustness of the network with an improvement of about 6%. So to summarize this long talk, in spite of the fact that we do not understand anything about deep networks and the theory is very far away, the attempts that we have done so far to sort of digest, to see what is going on, are far from being successful. But even simple observation give you hints on how to optimize the real machines that you work with. This is a paper that is being published in Nature Publishing Journal called Artificial Intelligence, and it came out a few days ago. There is a long road to go, and I thank you for your attention.